So real world CSPs, we were discussing actually the constraint satisfaction problems in our previous lecture, and we discussed some basic method to implement the constraint satisfaction problem, and that was, if you remember, these are some of the examples that we were discussing in CSP, that if we have to map the Australian territories with the three different unique colors and every adjacent territory should have the different color, which was the condition. So we designed this problem according to the variable domain and constraints, and then we solve using the CSP. And then n-coin problem, and then we discuss the two variations of n-coin problem, then this constraint of uh, consider this constraint graph carefully because we will be using this constraint graph today as well. And then some types of the constraints like unary constraints, binary constraints, and n-array constraints, then these state arithmetic problems. Sudoku example, and we were finally here on the slides. What are some real world examples of CSPs? Today we need to see the implementation approaches of CSP and some variations. I will start from here because I will try to build up the basic understanding that what's the difference between the simple implementation of constraint satisfaction problem and how we can improve the limitations of simple constraint satisfaction problem. So, considering this constraint graph for one of the problems are the examples that we considering is the Australian directories map. Okay, so what does this mean if we use BFS to do or to complete this task? It means it's very simple. Considering this constraint graph, if we apply BFS, it means that we will select this variable first. We will see how many values are there in the domain of this variable. So of course, because this is the first variable, so we have the options of red, blue, and green in the domain of this variable, and we need to assign any value to this variable. So what we will do, first of all, we will see that is there any unary constraint, because we are at this moment only considering first variable, the single variable, right? And then that is the Western Australian territory. So first of all, we will see that in the domain of this variable, out of red, blue, and green, is there any unary constraint that needs to be satisfied, or we can assign any of this color? So let's say if there is a unary constraint, means Western Australia territory, let's say, cannot have cannot have red color. If this is the unary constraint and we have this constraint in our list of constraints, so we cannot assign a red color in this case. So we will remove the red color from the domain available options for this territory. So now we have two options left. Either we can assign blue color or we can assign the green color. So if there is no unary constraint, we can assign any of these colors. Okay, so remember we are following the BFS. So once we assign, let's say, blue color to the Western Australia, then using BFS, we will go, of course, let's say, Southern Australia, right? And in the domain of Southern Australia, we have now two options left, red and green. There is no blue option because blue option has been assigned to one of the adjacent state. So the domain of this Southern Australia is red and green. We will check if there is any unary constraint. We will adjust the domain values to satisfy the unary constraint. If there is no unary constraint, of course, we are considering the binary constraint. This is the binary constraint. This is the arc. Arc always has the binary constraint because this is between two variables, Western Australia and Southern Australia. So out of these red and green, if there is no unary constraint, let's say we will assign the color red to the Southern Australia, Then because we are following BFS, we will come to this state, and the domain of this particular state has only one value, and that is green. Because the blue value has been assigned to one adjacent or the neighboring states, and red value has been assigned to the second adjacent or the neighboring states. So we have only a value in the domain side is the green, and if there is any unary constraint, we need to check that. Let's say if the unary constraint is Northern Territory cannot have the green color, which means there is no value available to assign. If there is no unary constraint, we can assign the green value to the Northern Territory. So let's say we are going to assign the green value to the Northern Territory. Because we are following BFS, we will come here, and for the variable v, we will check that what are the values available in the domain. So one of the adjacent states has red, so v has the option of blue, and v has the option of green. So out of these two values, we will assign any one value, and let's say it is blue. Okay, you can see for now there is no constraint violation. Then we will go to this state, let's say, and we will check the domain availability. So the values that are available for this is the green, right? So what we will do that we will assign the color green, because we can assign this green color. There is the blue color in one neighbor, then second neighbor has the red color, so we can assign the green color. Then we will go towards the state Q, and we'll see the domain of the Q, and the domain values of the Q will be, we cannot assign the green, we cannot assign the green. So we cannot assign red because red is another neighbor. Red, green cannot be assigned. We can assign blue, so we will assign blue to this territory. And you can see all the states of the territories has unique colors. And then of course, because this is outside of the graph, so at the end, this has all the three options available, which is going to be red, which is going to be green, which is going to be blue. So you can check the unique constraints. If there is no unique constraint violation, you can assign any one of the state. Let's say you can assign red, for example. So this is what this is how you can solve this problem of CSPs using BFS. But just imagine if there was the unary constraint this particular variable that Northern Territory cannot have green color. If this is the unary constraint on this state, of course we have only the value available that is green. We cannot assign green value. So in this particular case, there is no solution according to the previous values that we have assigned the neighbors. Western Australia blue, Southern Australia red. It means we cannot achieve our complete solution. We need to backtrack, we need to go back, we need to reassign. If this particular state has the unary constraint that Northern Territory cannot have green color, means we can assign green color to the Western Australia rather than the blue, and we can assign the Southern Australia blue rather than the red. And in this way, we will have the red option available and we can assign to the Northern Territory. But for that, we need to, of course, go back and reassign these values. And we need to see the backtracking today, how we can backtrack and solve the solutions. So if we talk about the DFS, we can of course solve using the DFS as well. For the DFS, we will repeat the steps. Just what? Yes, Muhib, go ahead quickly. We cannot listen. No voice. Again, I think पहले भी एक दिन आप हमारे कहीं इशू था। यस मोहिब, हमें आपकी आवाज मे बी आई हैव तो अनम्यूट होता है। I think you should the unmute control. You can unmute now.
थैंक यू सर। सर मैंने पूछना था कि जो आपने अभी हमें एग्जांपल दिखाया है इससे हम गोल को कैसे
Yes,
लोकेट करते हैं।
good. So goal is a very simple thing in CSPs, and that is going to be the, you can say, even a simple if condition. If your all variables, the dictionary of variables, let's say Western Australia, your Northern Territory, so far, your Tasmania, right? When your all variables has been assigned some of the values, and those values are not clashing or are not kind of violating any of the constraints those are available or those needs to be satisfied, then you have achieved the solution. That's the solution condition, or that's the goal condition. You need to check.
ओके सर।
If any variable left without assignment, you didn't achieve the goal state. If any variable has the value that is violating the any one of the constraints, so you did not achieve the goal solution. That's is a simple condition in the case of TSP. And in the case of DFS, what we can do, DFS will follow the depth first path. We will assign value to this variable first, then this variable, then this variable. Then we will go to the next depth, this variable, then this variable, then this variable. So just the sequence of assigning the values to the variables will be changed because of the DFS. Of course, this thing will make a lot of impact that what research we are going to use either DFS or BFS when we will backtrack. Remember, so when we will backtrack, it will have a very big impact. If we use the DFS and we backtrack and reassign values, and if we are using, let's say, the breadth first search and we are backtracking, there is a big difference of the complexity in both of these items. Okay, moving next. Uh, so what are the problems with the naive search? So the naive search, if the naive search like DFS or VFS don't have any backtracking, so the clear problem that we can see in the naive search is um, most of the times we will not be able to get the solution because as you see, if we assign the color blue, if we assign the color red, and only the green color left for the Northern Territory, and Northern Territory has the unitary constraint that Northern Territory cannot have the green color. So this is where your knife search will fail. You cannot assign this green color to another territory, which means you are not getting the solution. And if there is no backtracking, you are not going to even complete your problem. We'll stop here. So this is the problem in the naive search algorithms, DFS and BFS. So we need to see at how we can come up with the solution. And the first solution is the backtracking search discussed right now. Now we need to see in depth the backtracking because the simple backtracking is not going to be efficient. You will see why. So backtracking, course, we will use backtracking because if we don't use backtracking, most of the times we will not be able to get the complete solution. We will stop after some of the variable assignments. So backtracking will solve the problem of incomplete assignment. But variable backtracking search will increase the complexity in both ways, in the time complexity, in the space complexity. So we need to optimize the backtracking search. And for optimization, we have multiple variations that we need to consider in the backtracking search. We'll see in the next slides how we can improve our backtracking search. Of course, we need backtracking search because without backtracking search, our solutions are incomplete. Backtracking will help us to complete the solution, but in parallel, we want the optimal complete solutions. For the optimality or the efficiency of backtracking search, we will see some improvements in the backtracking search. So the idea to implement the backtracking search is we should assign one variable at a time, and when we are assigning the value to one variable at a time, we need to check the that the assignment is consistent. We will see this thing next. The second idea is check the constraints as you go. Like when we were assigning the values to this graph, I was assigning blue, I was assigning red. So the idea is we need to check whenever we assign um, what's possible value to a variable, we need to check the constraints in parallel. That this, this particular value to this variable is 100% constraint free, and and of course the next thing that we need to check is the remaining values that that are left in the um, domain set of this variable. Can we assign any other possible value? So of course for this we need to do some extra work. For example, for the first variable, why didn't we try the red and green as well? Maybe maybe red and green allocation is much better to Western Australia in terms of that that the next states or the neighboring states, the Northern Territory and Southern Australia, um, will have easy assignment. We have if we have the other values available in their domain. What does this mean is basically if we are assigning variable a value, we need to check that which value we can assign, which is going to be less conflicting uh, for the upcoming variables assignments. Of course, we need to see this in detail and then we'll yeah. And this step for search with these two improvements is called the backtracking search. So we are just calling this thing the backtracking search. As you can see, it is written there, not the best name. But of course, we are calling it backtracking because we are assigning one variable at a time and we are checking the constraints that the assignment that we are uh, doing to any variable is consistent at this moment. So what backtracking search is, for example, initially all the states, all the variables have zero assignment. So let's say the first variable have the choice of red, blue, and green. If we are following the DFS with backtracking, so we will select, let's say, red color, and the second possible variable have the two options. One is the green, and the second one is the blue. We will select any one of these options, and the next possible state or the variable has two options, red and blue. So we will select one of these. So in this way a complete graph, depth level graph will continue. So let's say you will select the red. So next, we will have the two options for the next state. And uh, let's say this is one of the states. So next, we will have the two options for the next state until or unless. Um, so where you will stop? You will stop if there is no value left for the assignment. Of course, you will stop. Or if there is any value that is available for the assignment, but it is violating the constraints. So you will stop at that point. Whatever the point where you will stop, you need to backtrack. No, there are two, three different options. Backtrack at least one step back and reassign. I mean, remove the assignment of this variable values so that you can assign rather than green, you can pick this path, blue, and move forward. Or maybe you can go two steps forward at this stage in the backtracking, and you can select rather than assigning first variable the red value, we are going to assign the first variable green value, and let's consider this forward. In this way, you will again go go down, go down, go down, go down. until or unless you again stuck with some constraint violation, you will again get back, again backtrack to this, or maybe backtrack to this. This time you considered no, in the first variable we should assign the blue color, and again moving next, moving next, moving next, moving next. So now you get the idea why a simple backtracking is very computational expensive, because you will select the one option, you will go ahead, go ahead, go ahead, go ahead until or unless you stuck with some constraint violation, you get back and choose the second option, and you go down again for the complete assignment, going forward, going forward, going forward. You again stuck with some no values left, or maybe some values those are um, violating the constraints, and you will come back again and select any third possible option. So backtracking search is very expensive. We can get the complete solution using the backtracking search, but backtracking, simple backtracking without the improvements, it is very expensive. So what we can make the improvements in the backtracking that our backtracking search is efficient are the optimal. We need to see this. So this is the backtracking algorithm. You can see in the lab, but I can go through maybe very easily for you. So the backtracking search, we have the recursive algorithm of the backtracking. You can clearly see initially there is the empty dictionary, or there is no variable um, in the dictionary that has been assigned any value. So we need to assign all variables best possible values considering the constraints. So what we will do in recursive function, we have the assignment variables, we have the constraints. So we will return either solution, either failure. So we will get, if the assignment is complete, then of course we will return this assignment. Assignment is actually the dictionary that is having the variables um, with their assigned values. So if the assignment is complete, all variables has been assigned a value, we can return the this assignment dictionary that, for example, uh, it will look like this. Example, this is the Northern Territory. We have assigned the value to Northern Territory is, let's say, a red, and second variable, second key, and that is the Western Australia, and we have assigned, let's say, the value, and that is blue. This so this is what it looked like. So if this assignment has the length of this dictionary is equal to the number of variables, and all variables has at least one value, and that one value is not constraining any of the available constraints, is not violating any of the available constraints, we will return this assignment that this is the best possible assignment. Remember, I give you the example of timetable scheduling and the date sheet. So consider that you are making the timetable for each class, for each section. So this section is the key, and the time that you are allocating is going to be the assignment. So once all the sections has been assigned, um, some of the time slots, uh, those are not clashing with any other time slots. So of course, we will return that this is the best possible assignment of the time slots for each section. Otherwise, what we will do, we will select the unassigned variable, whatever the variable that has been left so far, um, that is without the value. So we will get this variable, and once we have the variable, for example, the Southern Australia has no value yet assigned. So we will get this variable, then we will see the values, right? We will see the values from the domains, that what values are available to be assigned to Southern Australia. And once we get the value one by one, this is a for loop. We will get the value one by one from the whatever the values are available in the domain set. We will get the values one by one. So we will check each value. If the value is consistent, if the value is satisfying the constraints, then of course we will add the variable to this assignment list, assignment dictionary, that this variable has this value which is not violating any constraints. So this has been added to the dictionary. Otherwise, what we are going to do is And once we assign the variable a value which is consistent, we are going to call the recursive backtracking search. I will tell you this point. This point is very important. Why we will call this backtracking search again? Because um, uh, of course, we need to check that if this assignment is consistent or not. I will tell you it's later. So if the result coming back through this algorithm is okay, consistent, if result is not failure, so we will remove, we will return this result because this result has no failure. Uh, as I already mentioned, we need to see why we call this backtracking search. This is very important part. Once we assign a successful value to a variable, we need to check its conflicts with all of its neighbors. That is why we are calling the recursive backtracking. And we need to see this in detail in coming slides. And if the result of recursive backtracking is coming success, then we will return the result. Otherwise, if this is not successful, of course, we will remove the value from this variable and from the assignment, and this loop will come up with a new value. And if all of these values, those were available for the assignment to this variable, cannot be assigned, then we will return the failure. Hopefully, this algorithm helps you to understand. Yes, now we are at the step, and that is the how we can improve the backtracking. This thing is a little bit complicated, I would say, but I will try to explain you in very easy words. Let's see. These three things are very different. Three different, you can say actually three different ideas for the improvement of backtracking, for the efficiency of backtracking. One is the filtering, second one is the ordering, the third one is the structure. So structure is actually the quite straightforward thing. We are not going to discuss this in detail. Structure means that using the better data structure, using the better algorithm, and for example, using priority queue as compared to simple queue. So structure is basically problem formulation related thing. If you formulate your problem accurately, there are highly chances that you will be able to solve it easily. We need to focus on these two things. These two are quite conceptual or need to be understood. What is filtration and what is ordering? Okay, so Uh, let me tell you the filtration first. So filtration is basically, can we detect inevitable failure early? Uh, what does this mean? Remember, let's back. Yeah, I discussed this example with you, and I say that, for example, when we will do the first variable assignment. First variable has all the possible values to be assigned available in the domain set. You can assign red, you can assign blue, you can assign green, right? So of course, you need to pick one. So maybe you will pick the red color and you will go forward, you will go forward, you will go forward. And we discussed that if we have to backtrack, we will get back. We will see if we can assign blue color rather than red to this particular variable. And and then we will go forward. If this does not work, we will go back to the previous step again, and we will see, okay, rather than red, we should have the green color. And if this works, it's okay. Otherwise, you will again, after some computation, get back to this step again. And you will say, oh, okay, no, we should have considered the blue color rather than green. Maybe this will have no constraints next. So this is something which is making our backtracking very expensive because kind of we are doing the backtracking just like the uninformed searches. We are trying all possible options. So the first step is filtering. This says that uh, can we detect the inevitable failure early? Like if I select that, I'm going to choose the red color from the first variable's assignment. Can I detect very early that What about if I pick the green rather than the red? Because red may have some conflicting options in the next steps. Okay, let's consider the pick, pick the green one because green one has the less chances to have the conflicts list. Or maybe you can say, can we pick the blue color um, for the first variable assignment? Because we have three open options if there is no unary constraint for the first variable. We have three open options to be selected from. So can we select the blue if this blue will have less effects in the upcoming steps? This is what the important thing is. If we can map this thing accurately or correctly, this thing can make our backtracking less expensive because we need to backtrack in a very few cases in this particular scenario. I hope you got the overall point of the filtration. So, of course, I didn't discuss filtration in detail yet. We need to see in our next slides, but this is the idea that how filtration can help us. How we will actually implement it, we will see in coming slides. And ordering is very simple because you have studied so far different search algorithms and the graphs and many other things. You will get the idea better very quickly. So ordering is something. Ordering says two things. One thing is when I have a kind of okay. Let's go back. This to this graph. This graph will help you much more. Yeah. Consider this constraint graph. So of course, every problem that we are going to solve using the CSPs will have a constraint graph. You can draw the constraint graph for any particular problem. So considering this constraint graph, there are two things that needs to be important. One is if we are not using the BFS or DFS, we are using a plain backtracking option. So we have the options that after Western Australia, we can choose Northern Territory or we can choose the Southern Australia. So there are two options to choose. Next color. For example, first time I color the Western Australia, second time I can color the Northern Territory and I can also assign the color to the Southern Australia. So which state or the which territory should I assign the color second after the Western Australia? This is important. So this is going to be selected using ordering technique. I will tell you in detail when we will study the ordering. Second question is because we have the options available for the first is the red, green, and blue. And for this, if red has been assigned, we have green and blue. The same way we have green and blue, we have two options that we can select from these two choices. So these two things are important. The first one is what state or the what territory, the what variable next we need to assign after the first variable assignment. And second question is which value we should use if it is not kind of constraining, if it is not violating any unary constraint of this variable, which value we should pick, green or blue, because we have two options. So these two questions are important, and these are the actually ordering techniques. These can help you assign the better variables values first and the better values first. I mean, uh, you may be thinking some ideas about this, but it is very easy to understand that. So how we will select that which variable we will assign the next value and which value we will assign to the one selected variable. We need to see in the argument. Going forward, we are actually improving our backtracking search through the filtration and ordering. Let's see first the filtration. Okay, so filtration has the one concept that is there are three concepts in the filtration. The one is the forward checking, the second one is the consistency. And consistency itself has two, three different variations. The one is one consistency, R consistency, and then we have the K consistency, and then we have the M consistency. We will see it shortly. So filtration says that, remember the overall idea of the filtration that we studied. Can we detect inevitable failure? By the way, what could be the inevitable failure? Inevitable failure is the thing that if any variable's domain is zero, like if any variable's domain has left with no values for the assignment, this is the failure case. Are all the values that are available for the assignment are violating the constraints? This is the failure case. So how forward checking can solve this problem? We are saying that initially we have the three colors choices available for all the variables. We can assign red, green, blue to any of these states in the very first step. Of course, because we did not assign any value to any variable yet. So all these three options are very open to be assigned, right? So what we can do in this case? So forward checking says, let's say if if we assign the first variable, if we assign the first variable one value, and that is the, let's say, red value, so the Western Australia will have the red value. Forward checking says the connected states, those will be impacted because of this assignment, is this one and this one, because these are the neighboring states. The Northern Territory, this one, and the Southern Australia, this one. If we assign the red color to Western Australia, we cannot actually assign the red color to Northern Territory and Southern Australia. So why not? Let's remove this particular value from the domain of these two variables, right? This is what forward checking says. Okay, moving next. Next variable is, let's say we assigned the value to this. So why we selected this variable first? Why we assigned red color to this value? Remember, I told you that we will see this thing in ordering. On which order we will select this, that which variable we should assign the value first, and which value to be assigned to that variable. We will see this in the ordering stage. For now, let's consider we are selecting randomly, that we will first color this state, and then we will color this state. So for example, secondly, we are going to color this state, and this is the Queensland. So we will color this state, Queensland. This has been colored. So we will color the Queensland, and which value we will assign. We have three options for the Queensland, and let's say we have assigned the green color to the Queensland. So of course, the neighbors of the Queensland are the Northern Territory, and the Southern Australia, and the NSW. These three variables will be affected because these three are the neighbors. So if we assign green color to the Queensland, it means we cannot assign now even the green color to the Northern Territory. Red was already removed, so because of the Western Australia, we will remove the green as well. So blue is left, so green has been assigned. So from this neighbor, of course, green is left, and from this neighbor, of course, green is left. Got it? And next we will see that, okay, which color to assign to the next variable. Let's say we decided that this we will next select this variable for the assignment, v variable for the assignment, and v has all the three possible options available. We can assign any of these colors to the v, and let's say we assign v blue color, and the neighbor of v is NSW and SA. So SA cannot have the blue color, so we will remove the blue color from SA, and this is where the problem is, because the domain of Southern Australia territory has been zero, so no values left for the Southern Australia state. This is what forward checking helps actually. Forward checking says, so So we have a chain, we have a complete chain. It means if we assign the red color value to the Western Australia, the green color value to the Queensland, and the blue color value to the, if this assignment is inconsistent, this assignment is not good, as this assignment has left with zero values for Southern Australia. So we will see this thing before the assignment. That's why the name is forward checking. Once we will assign the red color to this state, we will see all these combinations. Yes, we will see all these combinations before head checking. Um, kind of we are thinking before the assignment or the allocation, rather than we assign, we perform these 10 to 15 steps and then backtrack. So this is what the forward checking is. But of course, this forward checking will will faster your backtracking search, but there are some problems with the forward checking. We need to see those problems. Consider this particular assignments. For example, we assign the Western Australia red color. So the Northern Territory and Southern Australia cannot have the red color, so we have removed the red color from Northern and the Southern, right? And next we colored the Queensland with green, so we have also removed the green from the neighboring states. Okay. Now, thing is, if we are going to choose the next variable for the assignment, in you can clearly see that the domain of Northern Territory and Southern Australia is not empty. There are still values, but the values that are available for the assignment are actually violating the constraint. We cannot assign the blue color to the Northern Territory and Southern Territory Australia. Both have one color available, blue and blue. Of course, we cannot do this assignment. This is the limitation of this is the limitation of forward checking. Forward checking was helping good in this way. We were able to detect that if the domain of any variable got empty, of course we will stop here and we will s- we will uh, explore other options of the assignment. Right at this step, you can see at this step, forward checking did not detect it. Forward checking went to the next step, and forward checking stopped at this step. But we should actually stop at this step because even at this stage, our um, our assignment has become inconsistent. So we should have stopped at this stage rather than going next. So this was the problem of the forward checking. So how we can solve, or we are going to further improve the forward checking limitation. That is through the consistency. Now, remember I told you that filtering has two different options next. The one is the forward checking, the second one is consistency, and consistency has its further three types: R consistency, N consistency, and K consistency. So we need to see the consistency now, how consistency can detect inevitable failures even before or even faster than the forward checking. So this is one of the example. How we can detect that we should stop here. This is what we call our consistency and how we can check actually. See this. Um, this is quite again complicated, but if you understand, you will get the idea. Our consistency says for this first we go towards the graph. I will get back. Yes. I will explain you the arc consistency from this slide and then we will see the example. Arc, remember I said here, this one connection is the arc. We called this connection the arc. So we need to make arcs consistent. What does this mean? This means If we assign this variable any value which is red, we need to check its neighbor through the arc, through this connection. And we need to check this neighbor through the arc, through this connection. And we need to see, okay, what values you have. I got the red value. Do you have other options, green or blue? Okay, yes, you have the other options, green and blue. So this state says yes. So this arc is consistent. If we assign green, so this arc is still consistent because this neighbor has red value. And this the state will ask this connected arc as well. Do you have any other value other than the red that you may have after my assignment? Let's say this state says I only have the red value in the domain available. So this arc is no more consistent. This is what the arc consistency is. Arc consistency says in our constraint satisfaction graph, each variable should ask the neighbors, if I have this value, do you have any other possible value for your assignment later on that will not violate any constraints? This thing is kind of a relational checking through the R. This thing will make inevitable failures detection more faster as compared to forward checking. In forward checking, we were just doing that until or unless there is any variable left with the zero domain values, we will stop in the forward checking. But our consistency says, I will go one step ahead. I'm not relying only this thing that if any next coming the variable has zero values, then I will stop. No, I will check. It is equal for me that if the next possible variable has some value, but that variable cannot get that value because of some unary constraint or because of my color coding. So it is still the point where we should. So this is what our consistency says. And the second important and good thing about our consistency is our consistency could be two-way. If this variable assign the value first, this variable can ask the value from this variable. And once this variable has selected any value, this variable can ask again this value to this variable. Okay, I have selected blue. Are you okay with this value assignment? And this variable can check this variable. This variable can check this arc, connected arcs. Are you okay with my blue variable? Did you have any other value that you will get after my blue assignment and there will be no conflicts, the constraint violations? So this is what the R consistency is. No, even at this step, let me tell you very clearly what is the difference between the three variations of R consistency. Uh, single R consistency, the K consistency, and N consistency. It is very easy. We call the R consistency when we are checking one connected neighbor. For example, Western Australia can check Northern Territory only, Northern Territory can check this one, and Western Australia can connect. So one immediate neighbor checking is called one R consistency. K consistency is increase this thing to at least two connections. For example, we will check from Northern Territory will check from Queensland, and Northern Territory will also check from Southern Australia. If we extend this R consistency to two next neighbors, this will call the K consistency. So this K value could be like 1, 2. In case of 1, it will become arc. In case of 2, it will become K consistency. And N consistencies, if we extend this connection checking of the arcs to the N number of neighbors. For example, by standing at this particular variable, we are checking that this arc is consistent. Okay, next check this arc is consistent. Okay, next check this arc is consistent or not. So this is what we call the inconsistency. Of course, it is complicated to implement the inconsistency. Okay, So we will focus more on arc consistency. At least arc consistency should be very clear because it is easy to implement and easy to check. We can go to a consistency. We will not be going towards the inconsistency because checking the n arcs consistent is NP hard computationally. It is very expensive. So move next. Let's see the example of single arc. What does this mean? See in the visualization. We will check Northern Territory. If Western Australia got the red color value, can Northern Territory have any value that can be assigned to Northern Territory, not violating any constraint? So yes, Northern Territory has the green and has the blue option. Most red cannot be assigned, but Northern Territory has two views. Those are not necessarily, those are not priority. Then we can check from the Queensland. Yes, Queensland has any value. If the Western Australia got the red value, yes, Queensland can have green or blue. Okay. If any arc is inconsistent, what we can do then? For example, if any arc is inconsistent, it means if any arc don't have any value that can be assigned to that variable, so then you need to delete from tail. This is important step. Please remember this. Deleting from tail means if any of these states those are available with the Queensland which will violate any constraint next in future, we need to delete that particular value from tail, not from the head. We are not saying that we will remove the assignment of Western Australia. No, we will remove the red from Queensland and red from Northern Territory because Northern Territory has two options, other green and blue, and Queensland also has other two options, green and blue. We should delete red from Queensland or Northern Territory, not from the Western Australia. So always delete from the tail. If you are checking the arc this way, from this neighbor to this neighbor, if this arc is inconsistent, we need to make this arc consistent. And for making this arc consistent, we need to remove the values from the tail, which can make in future this arc inconsistent of the value. So we need to delete those values from the arc. This is what the overall concept of arc consistency is. So you can see the example of Victoria and North Southern Territory, Southern Australia and North South Wales. Remember, I said the arc is two-way, so we need to check the two-way consistency and this is the algorithm of consistency. Now, what are the problems or the limitations of arc consistency? Remember, we see that there are some problems with the forward checking, so we need to see the arc consistency as well. And the problems of arc consistency is very easy, can have one solution left. When we are saying that we need to make every arc consistent, if any arc is inconsistent, we need to delete the values from the tail to make it consistent. When we are deleting the values from tail, there could be this option. We have left only with the one solution. Okay? And that one solution may have the unique state violation. This is the problem of arc consistency. Or we have left with the multiple solutions. Multiple solutions means this one, kind of a deadlock. We have make these arcs consistent. All these arcs are consistent. If this got red, this can get blue. If this can get blue, what variable will get? Because one neighbor is blue, second neighbor is red. If we see the arcs, both the assignment arcs are consistent. We are saying that we are saying that if I got blue, will you have any other value that you can get? We are asking from neighbors. Neighbor said yes. If you got blue, I can have red. This neighbor also says, okay, if you got blue, I can have red. Arcs are consistent, but the problem is kind of a deadlock situation. Is the limitation of arc consistency. If we check this from this neighbor, if this neighbor says, okay, if I got red value, do you have any value that you can get This neighbor says, yes, if you get red, I can get blue. This neighbor also says, okay, if you get red, I can get blue. So this arc is also consistent. This arc is also consistent. You can check from this neighbor as well. From this neighbor, from this neighbor. If I got blue value, did you have any other value? Yes, I have red. If I got blue value, did you have any other value? Yes, I will get red. So this arc is consistent. Even because of the arcs are consistent, we have the multiple solutions left. So this is again the limitation of arc consistency. Can have no solutions left means when you are making the arcs consistent, you are deleting the inconsistent values from the domains of the tail. You have deleted all the values. You have removed red, you have removed green to make the arc consistent, you have removed the blue. There is no value left. This element. So these are still the limitations of arc consistency. And of course, these limitations can be solved using the A consistency or using the N consistency. But yes, I already tell you that we will not be checking the N level consistency. It is pretty NP hard, the complicated problem. Because recording is on, uh, can you please give me 5 minutes more? I just want to conclude this lecture. Maybe what I can do is I can check your strength. I can mark you all. Attendance taking was on according to this, but I want to complete this lecture. You can see, you can join your other class, and I will share the recording because I want to complete the slides left. I hope it's okay. Yes. Please tell me if there is any issue. Otherwise, I would like to make this recording complete. Okay, I hope you guys have no issue. Then we move forward. I mean, again, if you have next class started and you have attendance related issues in that class, you can go and join your next class. I need just 5 to 7 minutes to complete this. Your attendance has already been tracked, and I will part for the feedback. Okay, moving next. Next thing is we see the limitations of R consistency. That is why we are going to see the K consistency. I have already explained you what is the K consistency. So one consistency is also called the node consistency, is also called when you satisfy all the unary constraints, it is called that node is consistent, and we call it one consistency. The two consistency is between the two nodes, is between the arc. Remember, this we call this an arc, and of course, this arc is connected with two nodes, two variables. So that is why we are calling it the path consistency. K consistency for each k number of nodes. If we make all the arcs consistent, we call it the consistency. And strong K consistencies again all the variables, all the k variables, those are involved in that um, the consistency, and we have make all those consistent. This are the super consistency. Yes, I need to discuss the ordering thing. That is why I was asking for some time. And remember what was ordering? Ordering was which variable we need to select next, and which variable, which value we will select next. One side. So uh, very easy two things. So for the selection of next variable, we call it variable ordering. For the selection of next value, we call it value ordering. So we will select next variable on the basis of minimum remaining values. What does this mean? This means, for example, if we first selected this variable and we assigned it the red color, what variable we will select next out of all these variables, all these territories, and we will assign the value. We will select that variable which has minimum remaining values in the domain, because let's say this territory has the only option left red, This territory has green and blue. This territory has green and blue. This territory has, let's say, red, green, and blue. All three options available. This has only red. This has green and blue, let's say. What, which state or the which variable we will select next? We will select the variable next after this assignment, which has the least or the minimum remaining value. The thing is, we are actually trying to fail as early as possible, ताकि हमें बैक ट्रैकिंग बहुत कम करनी पड़े. हम जल्दी फेल होना चाहते हैं. We want to see if we can do the allocation of red to this state. It's okay. Let's pick the next variable which has the minimum remaining values, so that we can check that can we assign this value to this. अगर हम इसी को नहीं assign कर सकते, we should, that's it. We should reassign this red. इसको इसी को red नहीं देना चाहिए, इसको कोई और कलर देना चाहिए, ताकि ताकि हम इसकी domain change हो जाएगी. If we assign the red value to this state, the domain of this variable will change. We will have other options, green and blue. So very simple thing, variable ordering. For selecting the variable, we will select the one which has minimum remaining value. Set. And for the selection of value, for the value ordering, we will select the value which is least constraining. What does this mean? This means if we have the options, if we have assigned the value red to this state, we have the options of green and blue for this state. We can assign green and blue both values to this state. Of course, for this state as well, we have the options for green and blue. Which we should select, green or blue? The one which has the least constraints. It means we should select the best possible value which is least constraining for the other upcoming future variables assignment. It will be better for those rather than selecting, for example, let me give you a very clear example. If this territory has a unary constraint that this territory cannot have the green assignment, and we selected green for this territory, this is wrong. We should select actually blue for this, because sorry, yes, green for this particular state, because we cannot assign green to this, and blue for this. If this state or this territory has a unary constraint that it could not be assigned the green value, so then we should assign green to this state. We should not assign blue to this state. If we assign blue to this state, there will be no option left for the blue value. There will be only two options, red and green for this state. Red and green are more constraining values as compared to blue. Blue is the less constraining value if we assign the state. This is what the variable ordering is. So all these was to improve the backtracking search, the filtration, the ordering, all these techniques was to improve our backtracking search. Um, in short form, we call minimum remaining value MRV, least constraining value LCV. That's it. Um, that's all related to the CSPs. CSP topic is quite complicated, I know, uh, but I try to kind of give you the best possible things as I can. I recorded all this lecture. I know a few students joined from the next section as well. I was just completing the recording. Let me stop recording and take your questions.